series. And, Todd, why don't you go ahead and introduce Justin?
Sure. Justin's an old colleague of mine from many years back. Excuse me. He's a research associate professor at the Desert Research Institute, extension of the Nevada System of Higher Education. His research is focused a lot on remote sensing, using a lot of land surface and energy balance modeling, integrated models of hydrologic systems. He's got a lot of big projects with the Bureau of Rec doing the Colorado River forecasts and ET estimates at pretty large scales, lots of projects with NASA, and he's a member of the Landsat science team. So he's kind of helping us keep that mission going straight. So with that, I will throw it to Justin.
Thanks much, Todd, for the introduction, and thanks everybody for joining the webinar. Really appreciate it. First, I'd like to thank my collaborators on this project, a host of folks from DRI and the Western Regional Climate Center, and John Abatsoglu's lab at University of Idaho. They've been really instrumental in everything I'll be talking about. And then finally, our collaborators at Google who really helped us get this cloud computing work off the ground that I'll be talking about. So just for an outline, I'm going to be talking about different timescales of drought, and then place-based drought monitoring, and then how we've gone with cloud computing for this place-based drought monitoring as well as regional drought monitoring, and then talk about the application that our groups at University of Idaho and here at DRI have developed called climateengine.org, and then finally I'll do a couple demos of Climate Engine. So first off, drought is pretty complex in that it has multiple drivers and develops and recovers at different timescales. And so you can have different types of drought happening at the same time. And so on the left here is basically the last 12 months of precipitation and temperature. It's this combined index called the Standardized Precipitation Evapotranspiration Index. So it combines both temperature and precipitation characteristics, and so you can see over the last 12 months all the red areas showing the current western drought, which is more of a long-term or what we would call perhaps a hydrologic drought. And on the right here are the last 3 months precipitation temperature or SPEI anomaly for August. 3 months leading up to August, and you can see that Nevada, Utah, a lot of the central western states have been exceptionally wet, and then we have the Pacific Northwest, which has been exceptionally dry. And so this shorter term drought or soil moisture type rangeland drought is happening at the same time where we have the hydrologic drought. So we can have wet rangeland conditions on top of very dire hydrologic conditions, which is basically what we have now. And these maps were developed with the West-Wide Drought Tracker, which is hosted here at the Western Regional Climate Center and put together mostly by John Abatsoglu and others here at DRI. And what we wanted to do was kind of make this process more dynamic and more live, more real time. These don't get updated but once a month, and we really wanted to be able to zoom in and really focus on, say, particular mountain ranges, particular farm areas, and pull out time series and have it be more up to date. So I'll talk about that here in just a little bit. So for regional rangeland drought assessments, this has been a really big deal this last summer. Here's a difference from average vegetation greenness derived from MODIS, NDVI, the Normalized Difference Vegetation Index. And so on the left, you can see April 1 through September 16, median NDVI difference from the average, where the climatology is the 2000 to 2015, April 1 through September 16th, CLIMO. And you can see that in western and northeastern Nevada, we have abnormally green conditions where vegetation vigor has been anomalously high due to the pretty spring and summer that we've had. And on the left here is August 16th through September 16th. So basically what I want to point out is that you can go from being abnormally green to abnormally dry very fast. So basically the vegetation dried out very fast, and some folks might call this a flash drought, but in the desert, you know, the flash droughts are real common. This is a real common thing that can occur if you have a wet spring, and then it goes back to normal conditions in the summer, which means that we don't have any rain. And so if we have a wet spring and early summer like we've had, you can have exceptionally good forage on the range. The ranchers want to get out there and put their cows out because the feed is great, but yet the U.S. Monitor map, like this year, will say that all these areas are in the D3 or D4 category, and the BLM uses that map to primarily determine grazing permits. And so the cattle have not been allowed on the range, even though the forage has been really good. However, that said, the forage dried out exceptionally fast over the last 60 days. So just something to consider. With these NDVI anomalies, you can see clearly in California the impact of the drought. All these big red blobs are fire scars, and so that's pretty neat that these all pop out. So as I was suggesting, we've been really wet this last spring and summer in the Southwest, and this is a new index that our group created called the Demand Drought Index. It's basically anomalies in reference ET, physically based reference ET based on the Pima-Monteith equation. And so this is the 90-day eddy ending in mid-August. So clearly showing those wet conditions that I was alluding to earlier. And then here's basically a 30-day eddy ending in September 30. And so you can see how the mid-summer period has been quite warm, and that anomalously high evaporative demand basically caused all that vegetation that I showed earlier to dry out exceptionally fast. So a lot of this is tied to evaporative demand in terms of how things change rapidly. So I just wanted to talk about that a little bit more, how we can use these multi-scalar drought indices to dig in and look at changes, and how we see in terms of change using remote sensing, whereas the U.S. Drought Monitor map is generally more of a hydrologic type driven drought indicator. And so here's the map released on September 29, showing, of course, drought conditions over much of Nevada and, of course, California. And on the right here is the change for the last month, well, ending at the end of September, so it's a one-month change map ending in September, end of September. And you can see that the map hasn't changed. But from the MODIS maps that I showed earlier of NDVI, there's very large changes. And so that just, I just wanted to point out that using remote sensing, and specifically place-based remote sensing, where you can actually zoom in, pull out time series, look at specific counties and even farms, is really powerful and really can complement the U.S. Drought Monitor different classes that are shown. So the point is that not one map fits all droughts, and this is a Western Governors Association slide that I took from a webinar series that the state engineer in Nevada, Jason King, did, and his point was that one map doesn't fit all sizes of drought, and that there are reasons why drought looks differently across the West, and it's really tied to variations in hydrology, legal structures, and water availability. And so remote sensing can really help understand these, what I would call different faces of drought. So here's an example, and I'm going to go through a series of examples showing how water policy and water sources really makes drought look different in different places. So this is Lovelock, Nevada. It's the Humboldt River Basin. There is no ground for irrigation. Lovelock is in the Humboldt Sink, so there's very shallow groundwater. It's extremely saline. It's a groundwater discharge area. There's a big playa just to the south. There's very little upstream storage. And so this area is extremely sensitive to hydrologic drought, and especially persistent hydrologic drought. So it's an alfalfa region. Every single field shown here is alfalfa. And so what's shown here is the growing season median NDVI, and we use Google Earth Engine to compute this. Google hosts the entire 40-plus year Landsat archive and provides a parallel cloud computing that I'll be talking about later. But the point is that you can clearly see how things have dried out. 2015, this growing season, there was absolutely no water delivery, and there are upstream junior groundwater pumpers that are getting full production, and so there's a lawsuit right now that the upstream junior groundwater pumpers are impacting more senior downstream surface water users. So here's just kind of an overview of some different areas throughout western Nevada to kind of show this water management aspect and impacts of drought that we can clearly see using place-based drought monitoring through remote. So Fallon, Nevada. Here, this is the growing season, or April 1 to about mid-growing season 2013. And then in the center panel, this is the same date range, but for 2015, median NDVI and all this. And then the difference between 2013 and 15. So you can see a lot of red here, which means negative, meaning that 2015 had less NDVI than 13. 13 was also a dry year, but there was a lot of upstream storage still on the Truckee River system reservoirs. So in 2015, Fallon got a couple irrigations, but very, very limited, hence why there's a bunch of red. So here's Carson, Smith, and Mason Valleys. This is right at the base of Sierra. Lake Tahoe is right over here. Carson Valley here is very sub-irrigated, very shallow groundwater. And so you can see that Carson Valley hasn't been that impacted by the current drought. They're high up on the river system, have more senior rights, whereas Mason Valley, it's on a different system. It's on the Walker River system. They have supplemental groundwater pumping. So when there's no surface water rights available, they can pump supplemental groundwater. And so you can see that Mason Valley hasn't been as impacted as, say, Lovelock, which is shown down in here, down on the bottom, which is 100% surface water driven. And so they've been impacted the most. So because of supplemental groundwater pumping in these different areas, these communities are kind of hanging on. That said, their pumping is now impacting the river flow, and so it's feedback effect where because they don't have surface water, they're pumping groundwater, which is impacting the surface water, and so now they're pumping even more groundwater because they don't have surface water. So it's a big deal, and we can dig in and look at these impacts. So just some close-ups here. Here's Mason Valley, difference from 2013 for this last year. There's been some water right buyouts that have happened, and a lot of fallowing, going on some new ag that's gone in that wasn't around in 2013. But the one thing I did want to show is out on the range here, out in the desert, you can see this, the impact of the spring and summer rains where the rangelands are greener than in 2013, while at the same time the irrigated ag is really taking a hit because there's no water in the river. Same thing in Lovelock. So this is a close-up of Lovelock. Very, very green out on the range near the ag. So the ranchers are happy, but the irrigators are sad. And just, goes to show how we can have different types of drought happening at the same time and in opposite directions. And, normally when you look at these big regional scale maps or veg dry type maps that are generally regional in nature, you can't zoom in and actually go take a look at this kind of stuff. So just to highlight this point a little bit more, and less focused on ag, but more on range. This is in central Nevada in the Desatoya Range, Smith Creek Ranch. There's a bunch of pinyon juniper up in here, and you can just see the impact of this year's drought relative to 2013 on the riparian zone, and also the pinyon juniper. So there's been a lot of pinyon juniper die-off this year because of the very, very low snowpack that we've received, and now we're basically in the third year. And because PJs have deeper roots, of course, than the grasses, they're more susceptible to this hydrologic type drought and didn't really respond to the spring and summer rains that we had, because that basically just got all evaporated and transpired, and so the PJs are still pretty stressed. Here's a series of riparian zone. This is called Indian Valley, Nevada. This has got the highest, this valley supports the largest sage-grouse lek in Nevada. Basically, the populations of sage-grouse here are the biggest in the state. And so the BLM wants to know, when creating sage-grouse refugia, which areas in this valley are most resilient to extended droughts. If we're going to put up fence and protect riparian areas, where do we protect? And we want to try to identify where the vegetation is persistent, even through these long periods of drought. And so you potentially identify areas such as here, and you can see how 2015 was quite a bit greener than these other years because of this relatively wet spring and summer that we've had. But we can finally dig in and identify some of these things with Landsat-based remote sensing. So just to further dig into impacts assessments and using Landsat to look at drought and other things like water management, and try to separate out the impacts of water management from drought, which is not always easy to do. This is Needle Point Spring. It's near Great Basin National Park, which is right here. There's several rivers down in the southern portion of Snake Valley. This is right on the Nevada-Utah border. This happens to be the area where Southern Nevada Water Authority has applications to pump groundwater and ship that water to Las Vegas. And so this is a very contentious area. And this spring, called Needle Point Spring, went dry in 2001. The BLM owns a stock water right to this spring, and the pumpers nearby likely caused the decline in the spring head here. And this is a water rights hearing that got held, and the ruling has yet to be written. But basically, what we did was compare our vegetation index time series shown here. So this is derived from Landsat, Landsat 5, 7, and 8, where we did a spatial average over the spring area to look at NDVI over time, and you can see that right around in 2001, the NDVI dropped dramatically. What's shown here is precipitation. This is water year precipitation, and you can see that the NDVI generally tracks precipitation except for this big drop, which also, I should say, tracks precipitation. That's part of the problem here, is that there's a big drought that started in around 2001. So is it the pumpers that caused the decline, or is it the drought? So we did an analysis where we looked at the pumping ramped up, the head at the spring declined as soon as the pumping ramped up, and so if you plot NDVI with the depth of groundwater at the spring, you can clearly see there's good correspondence. And of course there's some big spikes in here when we have big water years. But the bottom line is that when we start to look at things, what we call in complementary space, where there's a complementary relationship basically between reference evapotranspiration or Pemmican-Monteith and ET, or using NDVI as a proxy to ET. Generally, when ET goes up, reference ET goes down because of that feedback effect. When ET increases, we have more humidity in the air, less sensible heat flux because you have higher latent heat flux. Typically, when we have higher precipitation, you have lower solar radiation because there's more clouds, more precipitation, and higher humidity. And so this is called the complementary relationship. So what we did was just plot post-pumping and pre-pumping NDVI, and so for the same given amount of precipitation, you have much lower NDVI. USGS has modeled groundwater levels in this area and the impacts of the pumpers, and it's pretty clear that the pumpers caused this spring to go dry. The point I'm trying to make is that using remote sensing and paired with climate information, we can start to tease out the impacts of drought versus management. These are just some photos of the Needle Point Spring area. This is all greasewood and saltgrass out here, so phreatophytes, shallow groundwater, tap roots are tapped into the capillary fringe and the phreatic surface of the water table. This is what it looked like in '94, and then this is what it looked like after the pumping started in 2001 and the spring went dry. Although there was also a drought going on. But in general, it's like, well, how far in space is this impact extending? So that's where we went next, is creating spatial anomalies with Landsat to see kind of what this looks like in space. So this is the NDVI anomaly for June through August of 2014 relative to the full Landsat climatology from 1985 to 2014. Now, to do this locally on my box, my PC here, I'd have to have the whole Landsat archive, of course, and write a bunch of scripts to make these anomalies, and it takes a lot of time and storage and computing power to do that. And so we used Google Earth Engine to do this, and it really is changing the way we do things, and being able to combine the time series and the spatial analyses is really greatly enhancing our ability to rapidly evaluate the magnitude and spatial extent and causes of vegetation changes related to climate, land, and water management. So here you can see that these are all phreatophyte areas, and here where there's groundwater discharge, the high white reflectance here is salt on the soils. So very indicative of grease saltgrass environments, phreatophytes. And then up here, the elevation, the topography rises a little bit, and you get more xerophytes, more sagebrush, rabbit brush. And so over here, you can see the impact of the recent summer rains. We had an anomalously green vegetation, whereas in the phreatophyte areas where the vegetation's living off the shallow groundwater, we have anomalously low NDVI, even though it was a fairly wet spring and summer. So the groundwater levels have dropped and have affected the groundwater dependent ecosystems in these areas. And so to this cloud computing stuff, just to kind of recap on just what will be required to do this type of work where you look at Landsat scale anomalies. Basically, if I wanted to do this for the whole state, I need 24,000 images. That's the collection that exists between Landsat 5, 7, and 8 for Nevada, and we just can't handle that. And so we are relying on Google, who's ingested the full archive of Landsat as well as MODIS, and utilizing their cloud computing system. So, as I mentioned, Google Earth Engine, they have the entire archive of Landsat and MODIS, as well as a bunch of different climate data sets that they've relied on us to help them know about and ingest into their systems. So we have the Climate Forecast System Reanalysis, we have NLDAS, the North American Land Data Assimilation System, and then this bias-corrected and downscaled NLDAS data set called the U of I MET data set, developed by John Botziglu's group, as well as DayMet, and now they just loaded up GLS version 1 and 2. And so all this is in the cloud and available for us to access. And so basically what Earth Engine does is they break out these image collections, they call them, into lots of different units, and they parse out those units to thousands of different computers to process those units all simultaneously, and then stitches everything back together. And so there's a Python API application programming interface, as well as a JavaScript application interface, and the JavaScript API is called the Playground, and it's really great. You can just write JavaScript code to call in image collections, make simple computations, and it makes a map immediately. So this Landsat scale map, Landsat 8 NDVI for basically the growing season of 2014, basically took about 15 seconds to create. Now, Google Earth Engine doesn't actually process every single 30-meter pixel at a scale like this. It groups pixels together to a scale that is meaningful at this scale. You don't need to have 30-meter scale to get information out that's meaningful at this scale. So they aggregate to larger pixels and then do the computations. But as you zoom in, it resends those calls, and then it will do the computations at finer scales. So on to climateengine.org. What is this? It's basically a cloud computing and visualization of climate remote sensing data. It's a free application that allows users to access and process global climate remote sensing archives in the cloud. So this is a MODIS land surface temperature anomaly for the last 60 days. It was in a few seconds through our web application. So, you know, imagine trying to make this locally at your institution. It would just be a nightmare. So very, very neat developments. How did this started? Basically, we applied for a Google Faculty Research Award grant, and we were awarded to start a drought monitoring program using Google Earth Engine, and from drought it turned quickly into climate and remote sensing, and so it's a web application that allows the public to freely access and visualize all these things, maps and time series, and in near real time for drought, vegetation analyses, and most importantly, data discovery. And I have emphasis on data discovery because, you know, in the past we just haven't been able to explore what the data have to offer. And now we can see all these neat things. It's just really opening the door into all different types of things that we've really never been able to think about because we couldn't visualize it. So I just like to really emphasize that this is really changing how we conduct research by being able to see things and then generate hypotheses instead of you know, thinking about hypotheses and then trying to visualize what we're thinking about. So it's really changing the way we do things. And so it's a very collaboration between DRI and University of Idaho, between John's group and our group, and I'd just like to really give give hats off to Britta and Catherine at University of Idaho, and Britta here at DRI, and Charles Morton, and Dan McAvoy, and Donnie, and Alex, and Andrew, who are really the folks that have made this happen, especially Britta and Catherine. They've poured their hearts and souls into making this web application and work on it basically every day. So what is this thing? Web application relies on Google App Engine, which is basically the front end, and Google Maps API, and then Google Earth Engine is the back end. And so Google App Engine is linked to Earth Engine through the Python API and allows for on-demand parallel cloud computing. And so basically users input collection and time parameters through the Google App Engine, and then App Engine passes these parameters to Earth Engine in the back end, and then the results come back into the front end or Google App Engine. And so we set out with the Hello World SRT MDM App Engine example, and anybody can sign up for Google Earth Engine, and there's a developers forum, and if you want to make a web page that accesses Google Earth Engine collections and the cloud computing, anybody can do it. There's a developers forum that talks about how to make a page, and that's where this Hello World example is. We kind of took it to the next step fast, and it got complicated really fast. And we aren't professional web dev folks, and so it was definitely a big challenge for us, but we managed to plow through it and have made this application called Climate Engine, which I'll go through next. So we basically have a collection of different data sets available to access and process Landsat, MODIS, this U of I metadata, CFSR, and then CHIRPS precipitation, which is a global precipitation product, a pentad or 5-day time scale, and I believe it's 19-kilometer resolution. So you can access these different data sets, and once you pick a data set, then there's a whole host of different variables within the data set. So we have precip, temp, humidity, radiation. We have PEMIMON teeth, or physically based reference ET, PDSI, also with physically based reference ET used as the potential ET in PDSI instead of the typical Thornthwaite equation. Fire indices, veg indices, drought indices, snow cover, lots of different things depending on the different data set you pick. Custom statistics, so average, difference from average, percent difference from average, percent of average, and then we even have percent of in the distribution. And we're working on different non-parametric ways to depict drought and anomalies rather than using parametric distributions or things like SPEI with gamma distributions and things like that. So you can pick custom date ranges. And so here's just some applications that I'm going to run through. So here's the 2015 Sierra Nevada snowpack, median normalized difference snow index, difference from average for basically October through April, or to April for this last year. Everywhere in red should have been covered in snow, and it wasn't this last year. Pretty dire. Here's PDSI, January through June of 16. We have the USDM drought color ramp in here to make maps more visually comparative to the USDM map. Here's median land surface temperature, a difference from average for July through September. I really like to look at this land surface temperature anomaly type product because it gives you such a good sense of the land surface energy balance and evapotranspiration. Where you have cooler surface temperatures, you typically have higher evapotranspiration because that higher evapotranspiration in turn creates evaporative cooling and therefore surface temperature. So it really does tell a nice picture of latent heat flux. In fact, land surface energy balance models that compute ET, most of them are largely driven by surface temperature. temperature, and the relationship between surface temperature and T is extremely strong. So you can see here is that this abnormally wet summer, i.e. high evapotranspiration summer, but then embedded in here are all these little irrigated areas that I showed you before. Here's Lovelock, abnormally hot because there's no ET happening. Same with Mason and Smith Valleys. And then you can see a bunch of fire scars. This is the big fire that happened in Yosemite last year, year before. This is a big fire that happened near Pollock Pines. So really neat. You can see the decline in the Salt Lake. You can see the shoreline that should be covered with water, and it's not. So really intriguing things that you can see. Of course, the Central Valley is all dry because of the drought. So land surface temperature tells you so much about drought conditions and land surface energy balance feedbacks. So point locations, you can pull out time series for different points and then be able to plot those points together for intercomparison. You can plot the daily time series of MODIS and DVI or any climate product that we have. It's all the same functions for plotting. You just pick different data sets, basically. Intra-year comparisons, so you can look at within-year variability relative to the long-term average. And multiple-year comparisons, so you can start to say, hey, I just want to look at June through September for every year going back to 1985 to look at summertime effects for every year. So that's kind of nice. And then you can also draw polygons around, say, for example, a specific field, and then pull out the NDVI time series, spatially averaged time series for a field. And so what's shown here is an alfalfa field, and you can see the cuttings of alfalfa. Here are these spikes. These are cuttings. This is in Mason Valley, Nevada. But basically, these guys aren't being impacted by the drought because they're pumping groundwater. If I were to make a polygon in Lovelock, you'd see the cuttings, and then for the last 2 years, it'd basically be a flat line. So we can do field scale monitoring of vegetation, which is really new. So I'm going to do a couple demos now, and I'll give it a shot, see how it goes. So this is what's really neat is you can click on link here. Once you've made the map, you can click on the link, this link button, and it'll give you a link that then will basically embed all the map parameters, the web parameters into the URL, and will then go create the map for you in real time in the cloud. So let's see how this goes here. It's all right, so it is making the map right now. Now, I clicked on the link earlier, and so this results in the cache. That's why it's coming up so fast. These little squares that you're seeing, these are all results coming back from different computers at Google. But you can see the clear after the dry. You can see the range conditions. Now, I'm going to go to the north here a little bit and go upstream where there's groundwater pumpers. Now, Right Patch Reservoir is all green because there's no water in it, and there's a bunch of weeds growing in there now. But let's keep going upstream here, and we'll see all these center pivots that really aren't that red. So this is a big pumping area next to the Humboldt River called Winnemucca Farms, and most of their fields are abnormally green because well, we've had kind of a wet summer, and the evaporative demand's been fairly low, and so those crops are doing really well, and they're just pumping. So you can start to get a sense for who's being impacted by the drought and who's not. And the more you scroll around, the more calls go out to the Google Cloud, and we'll keep on doing the computations and pulling data. So pretty powerful stuff. Let's go back to my talk here and resume slideshow. Yeah, let's go to this western snow cover. I showed that earlier, but I want to show it again in more of a live version. All right, so it's making the computations now. Should be coming up. Okay, get map. Uh-oh, it's not working. All right, well, I'm going to go to these examples. So we have some examples on the page that you can check out. It hasn't been updated for a little while, but related to drought, I'll just show. Oh, well, first let's show this Eastern Polar Vortex 2. Why 2? Because in 2014 they said the same thing. Let's look at land surface temperature anomaly for this last winter. Pretty amazing what we can see here. How warm it was in the west and how just cold it was in the east. What's beautiful about this is a global thing. You know, they have the whole archive. So, you know, if you want to start to go global, it's very, very easy to do. So let's look at some more examples. Let's look at NDVI anomaly. This is focused on the Central Valley, I believe. Yeah, Central Valley data. So this is last year, the NDVI anomaly. So you can see the California drought. Now I didn't pre-run this, so that was not in the cache, and that's how this is coming up, using the full archive to calculate the anomaly. Let's do some more examples here. Let's do Texas and Oklahoma, Todd, since you're in Texas. Land surface temperature for 2011. Pretty amazing what we can see here. Of course, this is the big Texas drought in 2011 in Texas and Oklahoma. So pretty neat that shows up like it does. And then the Central Great Plains flash drought. Let's look at NDVI. This difference from long-term average. So yeah, here's that NDVI anomaly for the Central Great Plains flash drought for the growing season, May through September. Now I'm going to start a new session here. The climateengine.org takes you to it forwards you right now to climb-engine.appspot.com. Appspot is the Google front-end web service. But I'm going to zoom in to Needle Point Spring here just to show you how you can pull out a time series. Let's see here. I'm a little lost. All right, yeah, here we go. So here's this little blip on the map, Needle Point Spring. And I'm going to click time series, and it's going to drop a marker down. I'm going to put my marker right there. And daily data, yearly summaries, or year summaries. I'm going to pick yearly summaries and then go to Landsat 5. And I just want to look at the midsummer, August through September. If stuff's still green in August and September, you know the roots are getting groundwater. So I'm going to set my year range here. Landsat 5 ended in 2012, so I'm going to say get time series. So we'll cross our fingers as this works. I saw Britta's on the webinar. Britta is the brains behind everything time series on the page, and as well as Catherine. But all our plots are developed in charts. It's been a bit of a challenge to get everything working well. A lot of JavaScript programming and getting high charts to work. So right now it's computing the median for that date range for every year, and see that, yep, the spring started to decline vegetation vigor right when the pumping started in 2001. So really neat. We print out the time series here that you can grab. Now, if a lot of people want a reference ET for a location, MM-on-teeth reference ET for a particular location. So daily data over time period. I'm going to switch my data set to U of I metadata, and then I'm going to pick ASCE reference ET, grass reference ET, and I want a custom period, and say I want like a decade's worth. You can go all the way back to 1979 if you wish, and then get time series, and it will extract 4-kilometer resolution reference ET, MM-on-teeth based reference ET, and that fast. And then you can zoom in and look at particular time series, different types of plotting available. And then, of course, you can get all the data right here to pull into Excel or what have you. You can also share this link with somebody. So grab the link and say, hey, check this out, send it to your friend, and go from there. So, you know, this cloud computing with climate and remote sensing data has just really changed how we can access data and learn, and it's just really exciting. So, yeah, with that, little summary here. Drought happens at different time scales. Hydrologic versus soil moisture, rangeland drought impacts different sectors at the time. So ranchers happy that there's tons of forage. You got the irrigators that are really sad because there's no water. And the BLM that has to kind of manage all this and try to keep everybody happy. So hydrologic and rangeland drought can change quickly. So, for example, you know, if we have a bunch of atmospheric rivers coming in to the Sierra this year, the Tahoe and our Truckee River reservoirs, these smaller reservoirs and systems can fill up fast. On the other hand, we can have really anomalously high evaporative demand, and vegetation can dry out really fast, even though rangeland conditions may be favorable for parts of the year. So I'll just note that for bigger reservoir systems, of course, we're going to need many wet years in a row, like Lake Mead in the Colorado, to deal with that shortage. But cloud computing is really creating never imagined opportunities for climate remote sensing data discovery and applications, and especially place-based applications. I mean, most maps that use remote sensing right now for drought are very regional in nature. You can't zoom in and look at specific farm districts, can't pull out time series or particular pixels of interest at the 30-meter scale. So this is really allowing us to, this new cloud computing and web kind of front end is really allowing us to easily access dynamic and place-based data and products. And this is going to be especially useful for developing countries, drought monitoring in Africa, the famine early warning system called FuseNet group that are now starting to use this technology through our collaboration. And it's really helping students, professors, and managers and economists, and it's really an amazing teaching tool. One thing I forgot to point out that I'll probably get a question about that I need to point out here is that, for example, you can download these results. So that's the thing with this. It's like, let's use the cloud computing to generate the results we want and need, and then just download the results instead of having to become computer scientists to manage these huge archives. We really, as environmental scientists, just want the dang results. And so you can select download here, select the resolution you'd like, GeoTIFF. I'm going to draw a box here, a rectangular region, and so I can go download this NDVI anomaly map. So I'm going to hit download, and it's going to clip the result and then package it up with the GeoTIFF and send me to a link. You got to wait until it's done processing, and then go to the link, and it'll give me a save as window of the GeoTIFF. For whatever reason, that did not work. But anyways, it typically works. So point is that you can get the results and clip things out as a GeoTIFF. So with that, I'm wrapped up and happy to take any questions, comments, suggestions, feedback that you all might have. Let's see here. Should I try to answer some online questions, or?
Yeah, I think everybody's going to only have typing access, so they should pop up. And I can attest that the site, it's always created the geotips.
What's that?
It's always worked. Your website has always worked every time I've gone on there and made a geotiff.
Oh, good.
Crash you just had. Uncommon.
Yeah, it's inevitable they would crash during a live webinar, right?
Yeah, you knew it was going.
Let's try to make it happen again. Not going to give up yet. Yeah, there we go. Okay, so here comes some questions. Does this engine provide any future forecasting data? That's a great question. We've worked with Google to put in the MACA future climate data set. It's a downscaled and bias-corrected constructed analog type data set that's bias-corrected to NLDAS effectively, so it's 4-kilometer resolution. It's John Abatsoglu and Catherine's work. And so that is now in the cloud, and we have it ingested into Climate Engine. It's just that we have those options turned off right now in terms of the data set that you can select from. So I'm pretty sure we have it off on our development page. If you're ever curious kind of what we're up to, you can put -development here and go see climate. Oh yeah, we do have some future climate. Yep, we do have it in there. I thought Catherine had it excluded for a while, but we have the multi-adaptive constructed analog, the UVI data set, and then this NASA NEXT data set. So CMIT 5, the different climate scenarios. That's where we're going in the future, is to be able to pull out time series, make maps. It's on our development. In terms of forecasting, like seasonal forecasting information, like NMME type stuff, we're talking about going there, but Google hasn't ingested that data set into their cloud yet. Is the cloud computing software program free? How do I get it? You can sign up for Google Earth Engine. If you just Google Earth Engine, you'll go to the page, and on the right side, let me just show you how to do it actually as well. Google Earth Engine. Yeah, so if you haven't seen this page yet, it's fascinating. I just want to show you this time lapse before I show you where to go sign up. I know we're getting short on time here. So Landsat time lapse since 1985, anywhere on the planet. So this is Las Vegas growing, but the fascinating thing is it's anywhere around the planet. You can see Lake Mead dropping. This Walker Lake here. This is a terminal lake. All this agriculture in Mason Valley that I highlighted earlier is being diverted, and so the lake is declining. It's now a dead lake, meaning no fish because it's too salty. Just really fascinating. But anyways, let me go back here. So Earth Engine access, please let us know. If you want to be a Google Earth Engine partner, beta sign up, put it here, all your info. They'll give you a link to the playground, and then you'll have access to the JavaScript API and eeappspot.com. Let me just sign in another account. Allow. playground where you can code in JavaScript. So this is a CFSR test where we looked at just testing CFSR data, making sure it's making sense after they ingested it. So I highlighted a big atmospheric event. So here it run, it's going to plot precipitation intensity for February 8th of 2014. Now this is 6-hourly data, so but this is just as a test. I had just ingested CFSR, so I wanted to see if it made sense, and so I focused in on what I knew was a big AR, and so that's pretty neat. But it's all JavaScript. Within CFSR, you know, we have all these different variables: latent heat flux, sensible heat flux. It's global. It's, you know, over the oceans, which is really neat. So once you get access to Earth Engine, this is what you get access to. Basically, is this Python or JavaScript API called the Playground. Let's see, question. An amazing resource. Thanks for presenting. Thank you, Amy, and more thanks. So I think that is all I see for questions, and it's exactly 1 o'clock. So perfect. Any questions from anybody else, or you, Todd, or Emily?
No, thank you for the presentation. Very, very interesting, and slightly concerning, you know, the trends that are going on. I do want to remind all the participants that we have another speaker next Friday at 3 p.m. That'll be Brian Fuchs from the Drought Mitigation Laboratory at, hold on, let me make sure I get this right, at University of Nebraska. But that's it. I just wanted to remind everyone of next week's talk, and we'll be staying on the theme of drought.
Yeah, thanks, Justin, and thanks, Emily, for all your help.
Oh, yeah. You bet, and thanks, everybody, for your interest. And if you have any questions or want to know more about this stuff, feel free to email us. Thanks again.
All right. Thanks, Justin. Thanks, everybody.